Hello everyone. Let's start with something fun. Have you ever seen a figure skater spinning? Their arms and legs stretch out, but the spin has a rhythm that feels almost magical. That magic is explained by angular momentum. For a single particle, angular momentum is our cross P, the cross product of position vector and momentum. For many particles in a rigid body, we sum them all. L equals summation of our I cross pi. But here's the twist. The velocity of each particle depends on its distance from the axis, so angular momentum is not always perfectly aligned with the axis. It can tilt depending on mass distribution. Now let's focus on the part that matters most for fixed axis rotation, the component of angular momentum along the axis. For one particle at perpendicular distance are subscript perpendicular, the axial component Lz equals mr perpendicular squared times omega. For the whole body, these add up to Lz equals I omega, where I is the moment of inertia about the axis. This shows angular momentum is closely tied to how mass is spread out around the axis. Symmetry often simplifies life. In a symmetric body, like a disk or a cylinder, angular momentum aligns neatly with the axis, so we can simply write L equals I omega k hat. But if the body is asymmetric, things get trickier. Angular momentum may not point along the axis of rotation. That's why engineers carefully balance rotating machines, otherwise, the misaligned angular momentum can cause wobbling and instability. Now, how does angular momentum change with time? The golden rule is torque equals rate of change of angular momentum. For a fixed axis, only the torque component along the axis matters. So dLz by dt equals tau z. The perpendicular components remain constant since no torque acts along those directions. This is powerful. It tells us exactly which torques will alter rotational motion and which won't. Let's combine this with what we already know. If Lz equals I omega, then differentiating gives dLz by dt equals I alpha. But from torque law, tau z equals I alpha. Same result, just viewed from a different perspective. This is Newton's second law for rotation in action. Torque plays the same role here as force does in straight line motion. Time for a classic example. Picture a student sitting on a swivel chair holding dumbbells. They start spinning with arms folded. If they extend their arms, their moment of inertia increases. Now here's the law. Angular momentum, I omega, stays constant if no external torque acts. That means if I increases, omega decreases. The spin slows down. Fold the arms back, reduce I, and suddenly omega shoots up. The person spins faster. This is conservation of angular momentum at play. The same principle explains gymnasts tucking midair, divers flipping, or figure skaters dazzling the audience with lightning spins. So let's sum it all up. Angular momentum of a rigid body is the sum of our cross P for all particles. The axial component simplifies to Lz equals I omega. Symmetry ensures L aligns with the axis, asymmetry causes tilt. Torque along the axis changes angular momentum, while absence of torque ensures it is conserved. And conservation of angular momentum isn't just theory, it explains spins of skaters, acrobats, and even planets orbiting the sun. I hope this session gave you both the equations and the excitement behind angular momentum. See you in the next class, where we'll explore more on rotational motion and its deep connections with nature.